Okay. Yeah. Mhm.
Do you have some topic that you were wanting to discuss today, or you could discuss?
I was trying to review something around the idea of interaction that was the topic
Yes.
we were discussing last time.
Mhm.
But I have not time for prepare one presentation, but I have some ideas that maybe we can discuss about this.
Yes.
Mhm.
I'm especially motivated to understand a bit more how it can be applied to relativity,
Now, mhm.
yeah, because I I I have some ideas also related to what Oshevich was doing, especially in the relationship of the metric to the observer,
Mm,
like this.
mm,
And for me, I would like to be able to get rid of this notion of metric, um, and perhaps this interaction theory that you're working on is able to do that because it begins prior to the notion of geometry.
yeah. Um, the uh, I remember that I added one slide with the concept of observer that maybe can be the one starting point for this.
Yes, but I think that the notion of observer perhaps is a, a, a bit misleading, because I would I would like to be able to separate, say, the kinetic part of relativity and the dynamic part. And so the interaction theory would come into the dynamic part of relativity. Um, but I think that, yes, in keeping with Oshevich's philosophy, I would like that dynamics to be independent of the observer as such, so that it would be a kind of absolute
Yes.
dynamics. You know? And that, as far as I know, um, although Oshevich has, Zbigniew had some ideas about how to proceed, he didn't really have a complete um, theory of relativistic dynamics. He was just sort of starting to approach it, with the notions of center of inertia and so forth, and also discussing acceleration. But he was, I think he was distracted maybe by the fact that the definition of relative acceleration did not have any obvious connection to the dynamics. And so that relative acceleration is somehow connected to the observer and what you can measure, but it wasn't so clear how one should proceed from the idea of say acceleration as a Lie bracket of velocities, like how you would proceed with that to the idea of dynamic interactions.
Yeah. I was working around this, but my ideas is that first we is made the fundamental definition of dynamics in dynamics. And after of this, we can define set of concepts derived from this. And some of them are for the cinematical concepts, but those came from the observer viewpoint. And then we can formalize this in some kind of algebra. Then maybe I can put I am going to look this slide. One moment, please.
Okay.
Okay. I hope it is here. Okay, I have here now.
So far, I don't see your share yet.
Yes, it is going.
Ah, yes. Yes, now it's okay.
Okay, and now you can see the
yes.
first
Yes,
page.
that's good.
And then, excuse me, I'm going to go fast because
Sure.
It is not necessary to repeat some ideas that we were discussing before. And here is the idea of observer.
Okay.
Then the idea is that we have one of the objects in the category that are defined like observer. And through interaction, he is registration the state that he see for the other objects in the system.
Yes. So these interactions, I01, 02, 0n, these are the observations?
Yes, those are the observations. And C naught is the observer.
Yes. And now we also have this, I'm not sure what you call them, these identity arrows, like
okay.
I with the superscript n, superscript 2, superscript 1.
Yes, because I'm going to mark comments of this. Here, here is the interaction of phi 1 into C naught. And then if C naught register this interaction by this. No, excuse me, it was another, because the
Zero,
color.
one. Yeah. Yeah.
Yes.
Exactly.
Then this is the idea. The I not one, I am referring to this, is one point interaction. It is important because interaction have, I'm going to go to another slide before.
Let me ask first one question.
Okay.
So when we see this interaction I01, and we see this, I shouldn't call it identity, I suppose isomorphism, I superscript 1, 0. Should we think that, well, you spoke like that this isomorphism, how should we say, is it induced by the observation? So we say the observation causes this isomorphism?
Yes, yes, yes. This is, and you can see that I not one is one point action on C naught, but I0 one here is 2-point action in C naught. This is important because this is vector. Okay, this is candidate to vector, and this is covector. Because this 2-point interaction.
It says self-interaction.
This is the process that go from out of equilibrium in psi naught to equilibrium again. And for the formalization of this interaction in one algebra, this is important because then interaction is the product between the vector and covector. Maybe one multivector and multi-covector.
So this is covector. It looks like endomorphism on the states.
Yes.
Is that, but it's always a specific endomorphism on the state that takes the state from non-equilibrium to an equilibrium state. Is that?
Yes. Yes, this is the idea.
So equilibrium states are somehow special, right?
Yes, I remember that the idea of one measurement process is going from one equilibrium state to another equilibrium state.
Yes.
And then for this, we use this like a covector or a form.
Should I think of this as observation in the sense of representing knowledge, like so, in the sense that, or epistemology, right? So that we say that this observation results in some kind of change in our state of knowledge. So the equilibrium state that we were in before, say, didn't include any information about phi 1, but after the observation, then we have a new state in which we have some knowledge of phi 1, and then we cannot easily reverse this, right? It's not, we cannot say that we forget about this knowledge, that it's a sort of irreversible change, because we made this measurement and we have some knowledge now, and I'm thinking about quantum mechanics, I suppose. But the other possibility that I was thinking about is more in terms of dynamics, where like the actual absolute dynamics, which is referring to not to our information about something, but rather how the state of one object directly affects the state of another. Not in the sense of observation, but in the sense of interaction.
Yes, because when we speak about interaction, then I'm going to put this. This is this composition rule is I01 after I01. And this is the information. This connect the action of phi 1 with the change of a state in psi naught. And then this is the interaction of phi 1 into psi naught. We speak about observer because this is registration is made. It is going to register this information, and the registration of this information is the accumulation of knowledge.
Okay, so it's a when so you like this picture of the epistemology that this is a picture about how the information changes. But can we distinguish this between how the information changes and how the object itself is changed? For example,
excuse me, I don't understand how the
yes,
object.
I need to explain a little more, perhaps.
Mhm.
It's easier if we think of these as electrons, for example.
Yes.
If we think about these as human observers, like making observations or measuring instruments, for example, then it's not so clear what the distinction I'm making. But if we say that psi 0 is one electron and phi 1 is another electron, then we are suggesting that, say, the electron phi 1, it has some effect on the electron psi 0. Not so much that the electron is making a measurement, or that its information about phi 1 is changed. Like, do you see what I mean? I like to have these maybe at a lower level, where we can think of these as massive bodies, and that the type of state that they have is very limited, like is not a complicated state, but rather something rather simple, like perhaps a state of motion, for example, so that one electron affects another electron's state of motion. So this still fits your model of interaction, right? That the electrons interact, and as a result of that interaction, the motion of at least one of these electrons, if we focus at the one electron alone, then we say, because of this interaction, its motion changes. And in that sense, the change in the motion of the electron is how the interaction is registered.
Yeah, I see. But for example, you say this is phi 1 is one electron, and phi 2 is another electron. Then
Yes.
they are interacting between them while they are interacting between the one electron 1 and the observer. And the same is for the electron 2 with the observer. Then I think that we can imagine in this way. Using this process that we have here, we can register the one set of interactions between O and 1, and one set of interactions between O and 2. And then from this set of register, we can say something about the interaction between phi 1 and phi 2. But observer only can measure this, and this.
Yes, but still, can we put it at a lower level so that when we say that this electron, say electron 1, see if I can make a pointer here. How do I do this?
Okay.
Let me try new options. No. Thought there was some way that I could do that, annotations.
Maybe because it is not in the blackboard. I don't know if you can.
Okay. In previous times, I have been able to do that sharing, but when it's shared, it's possible in principle to be able to annotate someone else's shared screen. But at the moment, I'm having trouble to find how to do that. Yeah, in any case, I will try. So here we have these designations 0, 1, 2, and n. So suppose each of those objects represents an elementary massive body, such as the electron. Right? And so we distinguish one of these electrons, the one that's labeled 0, but I don't want to call it observer, except in the most sort of technical sense. I don't want to think of 0 as making measurements, but rather just as responding to interactions. So it responds in various ways, perhaps by changing its state. But the same applies reciprocally everywhere. But for this present, like for this discussion, we distinguish 0 as being the one that we focus on as being the one that's being affected by the other bodies. And we ignore for a while, as you have done here, you put only dashed lines, for example, around 1 and 2 and n. So we are not focusing on those things. We're only focusing on 0 and how 0 is affected by these other bodies, right? Now I think I'm just trying to recreate what you say, but in the language that I was hoping to use. So we would say, for example, that the electron 0 has some, say, time-like vector that describes its state of motion. And as a result of the interaction with electron 1, the interaction causes a change in that state of motion. So the electron 1 causes the electron 0 to accelerate in some sense, right? That there is a change in its time-like vector. So we say that there's a time-like vector here that is hidden inside this object that represents its state of motion. And then this isomorphism, endomorphism, that's associated with the interaction with 1 is a covector, and this covector, I think I would like to associate it with momentum, or something like this. That
Okay.
that it's the reason why I say momentum is that I'd like my goal, my objective would be to describe the dynamics as a Hamilton-Jacobi kind of relativistic equation, so that
Okay.
then this covector momentum is the exterior derivative of some scalar field, right? So that the usually you write this as S for the action, right? So it would be like ds is the momentum, but the actual dynamics would be something like, according to the Hamilton-Jacobi equation, it would be something like ds squared plus the some potential relating to the interaction. And of course, there's also mass in there, so it's ds squared over the mass is equal to or plus some energy that's related to the potential, and the potential, that energy related to the potential has to be what is due to the interaction with the electron one. So then so this tells us how this how the momentum changes. So the momentum is changed, but then I like the idea that you refer to a kind of return to equilibrium, because then we have to say, because the momentum has changed, the velocity changes as a result.
Okay, but I think that this idea is here. I don't know if it is better to go to one simple slide in where we have only two objects. Maybe the first here we have the interaction process between two particles, and we can see this in this way.
Shouldn't these endomorphisms here, like, shouldn't they have superscripts?
No, because I wanted to use superscripts only for observers and observations. Here, this O that we are using here is part of the interaction between phi 1 and phi naught. Because interaction is this I01 and I naught. This is interaction. Excuse me, it's, I think this is interaction. Mm-hmm.
But it's the same expression that you wrote on the previous slide.
Yes, but the difference is that one object is one observer, and then he make a registration of that process of interaction, because this first interaction, I am going to put here O1, and this is a process because when this is going, phi naught is going again to equilibrium, then in this moment interact with phi 1 and change the equilibrium of phi 1 that need to go again to equilibrium, and this change of equilibrium produce again one interaction from phi 1 to phi naught, and then phi naught is out of equilibrium, and then again go to equilibrium, and this is not only one process that begins and ends begins in phi 1 and ends in phi naught, but is a continuous process between the two particles that are looking like system go to equilibrium. And then this is interaction.
So do you write just I subscript 0? Does this mean that the object 0 is in equilibrium? It is identity as opposed to?
Not necessary, because I use only one index here by economy, because this is I naught naught, and here is I 1 1. Because here in phi 1 is one automorphism in this object, and I naught 1 is a morphism between phi 1 and phi naught. And I insist interaction is the composition between one morphism and one automorphism. Then I think that this can give to us the opportunity of express dynamic process between two particles.
So we have, okay, I understand I think I understand what you just said about dynamic process between two particles. But if we focus on just one of these particles, if we think in terms of just what is happening to 0,
okay,
then we are saying something like we are ignoring the blue arrows. We're not focusing on the blue arrows, but only look at the red arrows.
Okay.
Then we say that electron 1 changes the motion of electron 0 because of this interaction.
Okay.
so this is only part, as you said, it's only part of the dynamics. It's the dynamics from the point of view of electron zero. So this, of course, there can be the reciprocal statement about how zero affects one, but for just the initial discussion, if we focus just on how one affects zero, then should I'm not sure that I'm not sure about the distinction between the two types of endomorphisms that you've written here. Like in one case, you've written it with two subscripts, and in the other picture, the previous slide, you wrote it with a superscript, and you.
Yeah.
How should
the idea of right in the previous slide, like as superscript this index, was because I am thinking in speak about different observers. Then is one way of distinguish between different observers. But really, in the slide that we saw before, this was not necessary. This superscript was not necessary.
Because when we use this terminology observer, we tend to abstract the effect that the observer has on what is being observed, right? We don't focus on what the observation does to the object.
In classical mechanics.
In classical mechanics.
In classical mechanics, because in quantum mechanics is inevitable.
Yes.
Yeah.
But in classical relativity, maybe we can, like, without reference to quantum mechanics, if we just think about the relativistic dynamics without quantum mechanics, then with relativistic dynamics, we should be able to have a picture, I think, which ignores the effect that the observer has on the object.
Yes, in part, this was the idea in the previous slide when I put the rest of interactions in dashed lines. Because not only because maybe they are not important, but in fact, the observer ignore this part of interaction. He has not way of identify this at least he is making registration of this. For example, if we only speak about the red lines, then in a first process, I01 change the state of phi O, and I'm going to point to put here an upper index, the initial state, to phi 1. Then I am seeing now not this like object, but like a set of states. And then this is the change in phi naught, and then phi naught try to go to equilibrium again, taking this change to maybe phi 1 prime, because phi naught cannot not go back to the old state that he has. And then after he received a next interaction, and then he will go from phi 1 prime to phi naught, phi naught 2. And this is the process that in fact is we can describe like a scalar field referring to the different states that phi naught can have. Then the effect, the action of phi 1 is like a process here that is changing the state of the system, and this take from one equilibrium state phi 1 to another phi 2. Excuse me, I have to put like in the figure in this way. Then this is the idea with this description of process that we are making. And then in one out, this is phi, no, excuse me, this is I, no phi, is I 01. And then maybe with another process, I not, the system go again to equilibrium. Then interaction is from here to here. This is
but all the time we are focusing on zero, on the object 0.
Yes, all the time.
And
we are.
What object 0 is doing, right? And what's happening to object 0?
The object 0 is going either to equilibrium.
Mm-hmm.
And when he gets again equilibrium, he changes the condition in the system and then produce this interaction on phi 1.
But the dynamics should be describing this process. the dynamics should say how how object zero is changing because of the interaction, right?
Yes. And this is one of my ideas here. We speak about the change in the object that is observed, but the real effect is that we are describing how we change, how the observer changes.
Yes.
He or the equipment that he used for the observation.
Yes. So the interaction between 1 and 0 causes this change in 0.
Yes.
But our language that we used before is the opposite. You're saying that the so in a sense it's exactly backwards, right? That we say that the observer made an observation of how 1 changed, but
yes,
but rather the interaction between 1 and 0 says how 0 changed.
Yes, and this is the idea. Yes, I remember the observation in the LIGO observatory from gravitational waves, and then we register here in the Earth the one process in one black hole. But in fact, the change was here in the Earth. And we register that like if this was the change of the black hole. Then I am trying to build another viewpoint because the observation is one change in the observer. Observation is one change in observer.
I think I like, yes, I like this because, but still, the terminology observer is misleading for this reason, right? For exactly
Yes.
this reason, that the point of view is the opposite, right? The point of view is not so much about observation, but just purely about interaction. So in your example, we have this black hole, object 1, and it has some effect on instruments located on Earth.
Yes.
I0 or phi 0. And so we just describe this interaction. So we can make all that description without actually, how should I say, without exactly observing the black hole. Like we don't. It's not so much that we. Well, okay, maybe that's why your other picture was maybe better, but
I'm going to go to the other picture?
Well, I'm not sure, because you see, yes, maybe the other picture is good, but yes, go to the other picture, but I would like to suggest a change maybe, or
Okay.
okay, so
Maybe we can clean.
no, well, yeah, okay, sure, you can.
Oh, excuse me. I don't know. Better I left that.
Okay, no problem. So
Mm.
so here, instead of thinking that there are say 3 other objects besides the observer, suppose that these is just one other object, but in different states, so that this observer 0 is making some measurements, several different measurements, perhaps. So there is an instrument that registers gravitational interaction. There is an instrument that registers some electromagnetic interaction, like a radio telescope, for example, or there is perhaps another type of electromagnetic interaction is the optical telescope. So each of these 3 kinds of interactions with one other object, this object we call the black hole, because of these multiple interactions, we have the conclusion that we are measuring something. We are making an observation.
Okay.
If we just had a single interaction, if we just have the gravitational interaction, then this is maybe not sufficient to be called an observation, because we don't know enough about the object, right? See, I'm struggling with this idea of does observation mean a change in our knowledge, or does, see, interaction doesn't necessarily mean a change in knowledge, only a change in state.
Yes.
But in order to talk about observation, we need a more complicated situation, right?
But if I understood, you are saying that, for example, we have for phi1 a set of states that we are observing, and those are phi1, and excuse me, I need to do that for change the color here, I take some kind of depth in the interaction by phi2, for example. And those are the description of the state of the system.
Of a single system, though, right?
Of the single system, because these are a single system, for example. Mm-hmm. And I am making measurement about the one frequency emission in phi1 And in phi 2, maybe I am making one measurement about the electrical interaction, for example. And those are about the same system. Okay, this means that the interaction is more complex because the total interaction is making by I01 and I02. The idea is that this is related with one property of matter. And then this is related with the property of matter described by phi 1, and this is related with the another property of matter called phi 2. In this case, I have not two different electrons, but I have two different properties here in this system.
Yes.
Okay.
Let me, I also want to try to give a more concrete model, like, so is it okay if we make a model where these objects are, the state of the object is only represented by this, say, time-like vector in relativity? We would say that we have this time-like 4 vector, and it represents the state of motion, right? And so if you have here two different interactions with the same object, say a electromagnetic interaction and a gravitational interaction, we have just a second body, then we would like to know how those interactions affect the body zero, or how should we say it? It's always going to say, always we're going to be concerned about how the state of motion of zero changes because of these interactions. So the interaction in a classical or even in relativistic dynamics, we would say there's some potential associated with the with each interaction. Like each interaction is represented by no. Well, you said here that the interaction is represented by a vector, right?
Yes. Maybe by vector. I think that okay, here.
Yes.
We have one more concrete representation of this interaction.
Yes. Okay.
Okay. Because now interaction is this product.
So it's the evaluation
over differential form. and a multivector.
Okay, how do we relate that to the previous picture now?
Okay, because here is 2 points interaction. Then these 2 points interaction is one automorphism. No? This is automorphism. Then this is related with I not, for example. And this is related with I01. And the idea is that this gives to us one scalar field. And this scalar field is the description of the states of this system. Then we have here states. States, and this is expressed like an evaluation between a multiform and a multivector.
Yes, so this form, the form I01, it's what you wrote as an interact. Well, what did
you?
Yes, it connects two objects.
Yes, this is phi O.
Can you skip to the previous slide?
Yes.
Previous. Yeah, so 01 here, you labeled it vector, but on the slide we were just looking at, you labeled it form.
No, because I am here is the form.
With the superscript 1.
Yes.
Okay, so now return to this the most recent slide.
Mm-hmm.
So you should write this with superscript 1.
Okay, then I need to put the years here.
But you wrote X is an element of graded vector.
X.
No, okay, no, okay, I see. Yes, I understand.
Okay.
So,
I think that the index are wrong, and this is O, and this is 1. Okay.
yes, okay. Now, in a simple model of two bodies in motion, then we need to identify these uh, these objects in that, like with some math, like how should I say, we should give some physical interpretation to the mathematics, right? So that the vector x is say representing the relative velocity, say, between two bodies.
Here,
But alpha has to be representing a property of the object zero, right? So it's something like it's an intrinsic property of object zero. It like so
yes.
that so it is. I would like to say it's the momentum. It's the momentum of object zero.
Oh, okay. For example, this is
for example. So alpha is momentum, and x is the relative velocity, I think.
Okay.
Yeah,
but
so
in the idea of interaction, we need to relate here x with one process that changes momentum.
but it's a change of momentum of object zero, right? Yeah, it's okay, I think, because suppose we have some. We're not talking about observations at all, but just relativistic dynamics. So we have some relative velocity, but it's relative velocity in the absolute sense, in the sense in which Loschevich used absolute velocity as being a relationship between two bodies.
Yes.
So we just have this relationship between two bodies that's described by their relative velocity. And this relative velocity exists independently of whether it's observed or not. Like we don't have to have an observer. We just need to have two bodies. And when we have these two bodies, we can define the relative velocity between those two bodies. And that notion of relative velocity, maybe it's okay that it's this x, and that, but what's changing is the alpha, is the differential form associated with the object zero. So object zero's momentum changes because there is a certain relative velocity between 0 and 1. So for example, this relative velocity can be used to describe the electromagnetic field. So because we have two objects, 0 and 1, and we can describe some kind of electromagnetic field that can be split, right? In this electromagnetic field can be split into electric part and a magnetic part, and that these fields affect the momentum of object zero.
Okay. I was thinking, but in this, I can relate this like F, for example, and this better like Jack. And then interaction is a product between these two. That is related, for example, with the energy of electromagnetic field. or maybe like a Lorentz force of something like this.
So this suggests to think of alpha like current and X like field.
Yes, this is the idea behind this. Then, because I say this is a property of matter, this, and this is interaction field.
Yes, but I think
And I think that with this idea of interaction, we can define from this the laws of physics related to this.
I have one objection. I think maybe that this electromagnetic field should not be a relationship between two bodies, but the electromagnetic field should be a property of each body separately. But then as a result of the motion, the relative motion between the two bodies, and the presence of this electromagnetic field of each body, this is what is the Lorentz force, right?
Because the idea is that this expression of the property of matter are not dependent of the observer.
Yes, I agree, but that applies also to the electromagnetic field. Is not
yes,
the property of the
not
observer.
Dependent of the observer, not dependent.
But something that is dependent on the observer is the relative velocity. And the relative velocity in the presence of this field, electromagnetic field, is what gives the potential, right?
Yes.
It gives a electric potential and a magnetic potential, which is
because the idea here is to take the properties now from this mathematical object, differential form, and then relate this with the physical property laws, physical laws. Then we can put dl alpha equal, for example.
Yes. But so I would like to write that alpha is equal to ds. So S
Equal to.
I wish I could write. I want to be able to write on your screen, but I don't know why I cannot do that. How can I do that? One cannot write.
Maybe I
So-
can
so-
leave the screen to you, and maybe we can use the Blackboard.
Okay.
Okay.
Oh, I think now I think I understand what I was doing wrong. I did not see the annotation tool that I was looking for. But you okay? So you wrote that. Don't do that. So you wrote d alpha is 0, right? But I like to write alpha is equal to d of s.
Okay.
And that that this d of s, s is some scalar field called
The
Hamilton.
potential of alpha, for example. Mhm.
Yeah, well, let me write. What's this called? Hamilton's scalar. So this S, right? So we would write something like I'm having trouble to draw, but we would write. No, don't do that. Like D, yes. Can't draw it very well. Square is plus some potential is 0. And this so if alpha, so how else should I write? Sometimes it's easier to write if I wrote it in just classical mechanics, but not relativistic. So I'm trying. X. And then we can write that the D is Hamilton's expression that D is of X over m is equal to the velocity. So this is classical. But so the gradient of this of S is the momentum, right?
Okay.
And so that this Hamilton's equation, Hamilton-Jacobi equation, is just in the classical mechanics is just describing all dynamics in terms of a single field S, scalar field S. And so how this scalar field changes with time is what we call energy, and how this scalar field changes with space is what we call momentum. And all of dynamics is described just by this one equation. But in relativistic form, I mean, then we no longer distinguish time and space, and S is a scalar field over space-time. And but still the relativistic dynamics is described in the same way, essentially the same way. But here, the question that I have is what to put here, right? Like, so this potential is going to relate, say, to like in your picture, you had phi0, and you had phi1, and phi1 interacts here. But we like to say that that this object 0 is going to be associated with two things. Well, at least I want to say that it has both a velocity and a momentum. I don't know how to write. I should write maybe mu, right?
In fact, they are related. Then, but one is an intensive property, and the other is one extensive property.
But between these two bodies, 0 and 1, we have something like a relative velocity, 0, 1, and we have something associated with.
No, I think that here in the expression that you put, the potential B of X are the interaction between phi1 and phi0. This is the expression that corresponds to this arrow that you put there. And then we need one more arrow from phi naught to phi naught. And this is related with momentum of phi O. Then, in fact, the interaction between phi 1 on phi naught change the momentum of phi naught.
So we have this.
Yes. And this is the change of momentum, the gradient of S.
Okay.
But here we have not yet a relative velocity, because relative velocity
here not.
appears.
This, yes, I agree. Here, this momentum has nothing to do with relative velocity.
No, it's the change of a state of phi naught. The change of a state of phi naught.
Mm-hmm. But if we have another body, say body 1,
okay, mm-hmm.
then it has some. Now we can have a relative velocity between 0 and 1. And besides having this momentum, we would like to say that each of these bodies has its electromagnetic field, some also a property of the body 0.
Yes.
We have electromagnetic field F0 and we have electromagnetic field F1. And we also have this relative velocity between these two bodies. So now we would like to write the expression for the potential in terms of these two fields, F1 and F0, and V01, the relative velocity.
I think that the concept relative velocity only appears when we have two observers, or we have two bodies observers.
Yes, two bodies.
Two bodies that are observed. Then the relative velocity appears in a system of three bodies. One observer and two bodies are being observed.
So this arrow represented the interaction, right?
The interaction, yes. But the interaction, for example, here in terms of electromagnetic field produced by phi 1.
But we should know how phi 1 is moving.
No,
right?
Not yet.
If we don't know how phi 1 is moving, then we don't. How can we know what is the interaction?
Yes, because phi 1 is changing the state of phi naught.
But how phi 1 moves affects how the state of phi zero changes.
We don't know, but after of this first interaction, the interaction value change, and then we can say that the body phi 1 is moving. But after that, the interaction value have experienced one change.
But you see what I like to know is like how to like how to write this, right? So I can assume these dynamics. So we say,
because I think that we can speak about the relative velocity if we add one more body, and then we can speak about relative velocity between these two bodies observed by phi naught.
Yeah, let's see. I would like dynamics not to have anything to do with observer. So I would like absolute dynamics. So it's not necessary to have observer.
Yes, here there is a problem because in fact we can not put out the observer. we cannot put away the observer because he is registration the change of the entorn, and then he are making science, and when different observers are interchanging information, they went to some agreement, and then say, okay, here we have one physical law.
But see, then in your description, you return to this epistemology, to what the human being is making a theory, right? And that the activity of a human being making a theory is something like we just, psychologically we talk about as observer. Is yes. What the observer is doing is building a model of reality or something like this, right? But Shevitz wanted to say that reality exists without the observer, right? So it's like Einstein said that the moon exists whether I look at the moon or not. I like to think that even before human beings on Earth, there was the moon around the Earth, right? Without humans, without any observation, there is, first of all, some kind of absolute dynamics.
But if the moon not affects the Earth, we can make, we can know about the existence of moon, and then we can have one theory about his movement or something like this.
Yes.
And then I think that we can speak about the existence of moon after that we have get the knowledge about the effects of moon over the human. And then we can build some models for describe their comportament.
This is information about what we can know, though. It's not information about what is real. You know, so
yes,
so it's like
because I think that we cannot define what is real. We cannot do that. What is reality? And we only are describing the phenomena that we are experiencing, and then we build models for this purpose. I think that this is the this is my viewpoint.
But over time, this philosophy about physics, right, is that over time physics is about nature, right? Is about the idea that physics begins with observation and begins with making models, but tries to approach making each time stepping towards models that are more absolute, right? That are more about reality and less about what we're able to know about reality. It's the same as we're discussing for a few months now with Dr. Santilli about the Einstein, Rosen, and Podolsky. And so there was like Bohr, when quantum mechanics was being discussed, Bohr insisted that quantum mechanics was just about what we could know, you know, so that it wasn't about what was real, as you said. But Einstein had a very different view, right? He said that he wanted physics to be about what was real, and not limited by just what we can know about it, but only limited by our imagination, right? So we could I'm not sure
I think that the problem starts when we speak about reality, like that we receive through our eyes, for example. And then we qualify those like reality. But our eyes are a limit instrument. And then we cannot say that all that we can see is reality, because there are many things that we can see. Many. And I think that the problem that Galileo put in front of us when he used the telescope, then he's getting information through one instrument and not directly for or eyes, but using one instrument, he is getting information about the moons of Jupiter, for example. And for first time, we have to accept that there are more things that we can describe, and then we incorporate this information in the knowledge that we have. And then after Newton built the gravitational theory based on something of this observation. And we thought during many years that those was the reality. But Einstein, after, changed all general relativity proposal, and then those changed the idea of reality that we have. Then I think that it is because, in fact, we are observers, and then we describe the change of the around by the change of ourselves. And then I think that this is, we need one change of approach to this problem of interaction, because in fact we are describing change of states of us or of instruments that we use, and then this is the kind of knowledge that we can get by now.
But this picture that you just described, you assume that this picture is making a statement about reality, like in some sense, right? That this notion of state and change of state is something that is real, like not just something that is measured, but something that is a at least abstract statement of what is real. So the dynamics that I was trying to write down here, it is sort of similar in the sense that it is about how the state changes, how we describe this state changing, in a sense, in some absolute way, not like within this context we could say what is measurement, but we don't start with measurement, right? So that we try to build the dynamics that includes the possibility of measurement, because measurement and observation is something that complicated systems can do. So human beings can make measurements, and they can, their internal state changes in a very complicated way. But even before this possibility, even before the possibility that we have complicated systems that make measurements, even prior to this, I would like to think that there is a notion of state and a notion of how state changes, say even at the level of the most elementary particle. There is some simple primitive notion of state and how the state of that primitive object changes, completely independently of how we measure it, whether we measure it or not. Measurement only comes later, in the sense that once we know how one electron interacts with another and how we can construct atoms, and then atoms can encode information, and then, etc. Then later we can have instruments that the state represents some acquisition of knowledge in some sense, right? That is encoded somehow in a computer system or in a human brain or something like that. So the information, the theory of how this information is collected and manipulated is not the same level, and is a different kind of theory than the kind of theory that we started with about the dynamics that said how one electron affects another electron, how one electron interacts with another electron. And so that's why I'm keep trying to say, can we look at the interaction theory that you presented as a guide as to how to write such absolute dynamics at the elementary.
Yes, I think that we have here one hypothesis that you mentioned before is that one systems try to go either to one equilibrium state. This is one general assumption about this. And then if we accept that, we can say that the state can be described by a scalar field. Then I am going to the mathematical world and take some theory that will help to us to describe this equilibrium state. And after, we can speak about interaction like morphisms that are changing those equilibrium states. And then those morphisms are related with the physical laws. And I say that those expressions are physical laws only because until now the human is present in the earth and not more, not more, because this is this is because these expressions are related with reality, because if they are related with reality, they can permit to the human exist until now. Then I think that this is the our idea of reality. No? Reality, because when we proceed in this way, we still stay in the universe. No? And I think that this is the problem. My problem is that when somebody speaks about reality, I can find one solid definition of reality, and then when we try to relate this with the reality, but I need more elements for that.
Well, yeah, I know we're getting into more philosophical discussion, but I think it's here's my opinion, right? Is that we cannot speak about reality as if it's a single thing. So I I accept your view that reality is what we construct as reality is something that human beings build, right? Um, but there's something that's very important is that um, certain models are sufficiently rich that they are equivalent to other models. So so it means we have some alien extraterrestrial many light years away, and they evolve on some planet, and they make their own reality, right? But if their reality understanding of reality is sufficiently complex and rich, then there exists a mapping between their reality and our reality, right? So there's a kind of universality, right? That if the understanding is deep enough and rich enough, then even though the realities are different, they are equivalent in some sense. It's the same thing that happens in the abstract in mathematics, in the abstract theory of computation. It seems a strange connection, but in the theory of computation, there is a notion of computation universality. That is that any device that's equivalent to a Turing machine, right, can make exactly the same calculations that like say as you can make with the symbolic system of recursive functions, for example, right? So we have, even though there are different ways of building a computer, that ultimately all of these computers are equivalent in some abstract sense. Like there is a sense in which computation exists as a concept independently of how it's embodied in a particular piece of hardware. So the same thing is happening in physics, I think, is that even though we make models, and some models are partial, so we have like Newton's model of gravity, or we have Einstein's general relativity, or they are only partial. But in spite of the fact that they're partial, they are approaching something that is potentially universal. Right? So if you make it sufficiently rich, then it will be universal. That's it's how should I say this? Like it's kind of like saying that the overall sort of metaphysical approach is to say that mathematics is discovered, not invented, right? So that mathematics isn't just a human invention, that instead mathematics exists in some kind of universal sense, in that we approach this mathematics in our attempts to abstract the ways of thinking. We are actually reaching some sort of absolute ideal, some Platonic sort of concept. And so that when physics uses mathematics in certain ways, that's one of the objectives, is that we try to get the physics to be both abstract and sufficiently rich, so that if we move far enough in that direction, then we end up with something that we should should, for all intents and purposes, say we're approaching reality if we can approach this universality, right? So that we don't necessarily know whether this is exactly what is real or not, but our model of reality is sufficiently rich that it's equivalent to any other model of reality. And as you get into physics, it gets more harder and harder to say something that sounds sensible, you know. So anyway, that's why I justify that we should continue with sort of Einstein's program of saying what is real, like what is not just what can we observe, not just what can we measure, or not even just what can we know, but rather getting towards what is sort of some universal fundamental underlying structure.
Yes. I think that the problem in mathematics is a good example of this, is that the evolution of this language is clear. It is changing continuously. And then we now know that many times we have structures, mathematical structures that have different kind of axioms. And if we change those axioms, then the mathematical approach changes. Okay, it is difficult and dangerous idea, because we go inside of philosophy